Hi everyone. Today we're going to continue working through integration. We're going to continue with our u substitution, but it's not going to be quite as apparent what we should choose for our u in these cases. So let's start with our first example here. Let's say I have the integral of dx over x natural log of x. This is not how we're used to seeing these types of integrals written, but that's okay. We know that dx is just some very small amount representing a change in x. So I don't want it as part of my fraction though, because it kind of weirds me out when it's up there. I feel like it should be back here. And so if I want to pull it back here, I can do that. I'll just rewrite it as the integral of 1 over x natural log x dx. And this makes me feel much more comfortable. This is how it should be. I like that. You can keep it like this as long as you know that it means this same thing. And now it's time to figure out our u substitution. Here are the choices that we have for our u. I'm going to lay them out for you. We'll have 4 choices in this particular example. And then we'll have to just pick which one's the right one. The first one, and most obvious, is just let u be x, right? This is bad. This is never the right u substitution, ever. Don't ever do this. Here's why. If you say u is x, then we literally do not change this integral at all. It gets no easier, no better. It looks exactly the same, except instead of x's, there are u's. This is horrible. Don't ever do it. Well, all right, so we've ruled that one out. That seems fine. Our other 3 choices are, well, 1 over x, because here's 1 over x. Well, we could do natural log of x. We could do, I guess, 1 over natural log of x. And I guess the 5th choice that I didn't even think about until right now is 1 over x natural log of x. Now let's start ruling these ones out. So again, just like with the first one, the last one doesn't seem to make any sense here. We've just picked the entire thing to be u. Sometimes this will work out, but let's just go through systematically and see which one works out. If we want u to be one of these, then somehow solving for dx by taking the derivative of both sides should show us things canceling out. Let's explore and see which one works. If I let u be 1 over x, then du dx is negative 1 over x squared. That means dx is just negative x squared du. And the question that I'll have is there anything in here that will cancel out a negative x squared? If you answer no, then this is not the right u substitution. Because remember, we can't still have u's and x's when we do our u substitution. And if you tried this, which is a totally valid substitution, it won't help us integrate this function. Nothing cancels out the natural log. And I've also introduced a new term that doesn't cancel out either. So option 2 doesn't work out. Option 3, just natural log x. Well, here du dx is 1 over x. That means that dx is x du. So if I replace natural log with u, okay, so that's gone. This x would cancel with that x. Hey, that's great. So right away I've found, okay, this one definitely works. When you're doing u substitution, it might be the case that there are multiple u's that work. But if you find one that's nice and simple and works, just go with it. Okay, that's my advice. So let's tidy this up a bit. I've found the right u sub. Here it is. U should be natural log x. So these other ones I'm just going to kind of get rid of here. All right, so u is natural log of x. So let's rewrite this integral. It becomes the integral of 1 over xu times x du. This is good, right? My x's will cancel out. Everybody's happy. So this now becomes the integral of 1 over u du, which is natural log absolute value u, which is just natural log absolute value of natural log x plus c. Sorry. Oops. Forgot that my u's are all gone. And there we go. Natural log of x. And again, we can test this out. What's the derivative of log x? Well, it's 1 over x. Oh, sorry, it's 1 over log x times 1 over x, which is exactly what we had here. Whew. All right. So again, these ones just take a bit of time. We'll try one more, and then we'll see if we can generalize to figure out how to pick the right u. So let's see here. Let's say we have the integral of sine x cosine x dx. Again, there's no readily apparent inside function for me to use. So I'll have my three choices here. Choice 1, u is x. Choice 2, u is sine x. Choice 3, u is cosine x. I'm not going to list as a choice u is this whole thing. It could be, but not in this case, and that's fine. Option 1, u equals x. Again, this is horrible. Don't do it, right? It doesn't change anything about our integral. It doesn't make it easier in any way. If u is sine x, that means du dx is cosine x, which means that dx is 1 over cosine x du. And this is really good, because if I replace sine with u, and I replace dx with 1 over cosine x du, then my cosines cancel. Hey, that works out perfectly. It turns out that in this example, we could also have used u equals cosine x, but this happened to be the first one I used and tested and worked, so this is the one that I'll go with. This integral here now became the integral of u times cosine x times 1 over cosine x du, which is just the integral of u du, and that is 1/2 u squared plus c. And we recall that our u was sine x, so this is just 1/2 sine squared x plus c. Great. Hopefully that's not too bad. And here's the point where we'll pause and figure out what the pattern is. So in our last example, which we had 1 over x, natural log x, and in our current example, sine cosine. For here we picked u to be sine. Here we picked u to be natural log. What was nice about these choices is that the derivative of u also appeared in our integrand. Right? In this case, the derivative of u is cosine. It appears right there. In this case, the derivative of natural log was 1 over x, and it appeared right there. So choosing our u so that the derivative is also a part of the integrand is exactly what we want to do. That way, the derivative will cancel out with 1 over the derivative, what we get when we solve for dx. Okay? So let's try one more using this same kind of method. Let's say we're trying to find the integral of secant squared tangent. Okay. Again, I have lots of choices for my u. I guess there are 5 in this case. I could have it be x, I could have it be secant x, I could have it be secant squared x, I could have it be tangent x, or I could have it be secant squared tan x. Of those options, I should look at this and say, hey look, if I pick u to be tan x, how convenient it is that the derivative of tan x, which is secant squared, is also right here. Okay. This is so nice, because if I pick u to be tan x, then du dx is secant squared x, which means dx is 1 over secant squared x du. And now the secant squareds will cancel. So my new integral, when everything is substituted, will just become the integral of u du. Oh my goodness, how nice is that? This is always the most beautiful one, right? And so when we get that, again we have 1/2 u squared plus c, and again u was just tan x. Again, here's the deal. We could have picked u to be secant x if we wanted to, because the derivative of secant x is secant tangent. And so that's also appearing in this integrand. The difference between choosing u to be secant and choosing u to be tangent is the difference that you get here with the Pythagorean identity. So we perhaps remember that tan squared is equal to secant squared minus 1. So subbing that in here, you could manipulate this and get many different answers, right? You could write this as sine squared over cosine squared if you wanted to. There are different answers, but they're all equivalent. Okay. Great. So far, here are our options. Here are the things that we've done with u substitution. U sub. Our first method is pick u to be the inside function. This is not always possible. Sometimes there's no inside function, and that's okay. Our second option is to pick u so that du dx is also in the integrand. These are our two options so far, and they work almost every time. Almost every time. I'm about to show you an example where it doesn't quite work, and so we'll figure out a third strategy here. Let's do this example off to the side here so that I can add the third strategy right here. And this example will be, I'm taking the integral of x over x plus 1 dx. Now this looks very similar to some other ones that we've seen, but it's not quite. Right? If we pick our u to be the inside function, this is almost always what I want to do. And the inside function here is the denominator, which is x plus 1. And so that means u is going to be x plus 1. So du dx is just 1. Or dx is the same as du. Now this becomes a problem because then the integral simplifies to x over u du. And oh, man. But no matter what I pick for u, I can't get rid of that x. I can't get rid of it, right? If I picked 1 over x plus 1 to be my u, then the derivatives don't match and it's bad and nothing cancels. But after like days of crying, I have figured out a very, very clever solution to this problem that I didn't originally see. That is, I can turn this x into u's because I know that u is equal to x plus 1. That means that x is equal to u minus 1. So I can replace that x in the top with this nice equation here, and I'll get u minus 1 over u du. How cool is that? Hopefully pretty cool. I think it's cool. It's also clever. It doesn't jump out at you that should happen. we're so fixed on, okay, u, du, got it, that we forget that there are other things that we can do. And here, we have a difference in our numerator, which means we should pull it apart into two fractions. So I'll get the integral of u over u minus 1 over u du. Well, u over u, awesome, that's just 1. And 1 over u, I can integrate. So this becomes u minus natural log absolute value of u plus c. And then I'll just go back and plug in my values here. This is x plus 1 minus natural log absolute value x plus 1 plus c. Now here's the thing though. Writing x plus 1 plus c is odd because c is our constant term that kind of ends the whole function. So more often than not, we won't write a plus some number and also a plus c, but we'll absorb that one into the constant that we have formed. So I'm going to erase this one. If c is a constant and 1 is a constant, then c plus 1 is also a constant. And maybe instead of calling him c, I'll call him, I don't know, k for constant. Okay, so a different constant, but all the same, still some constant. And this is really nifty. This process, which I don't know if it has an actual name, I'll call it back substitution. This is a process called back substitution because you substitute first and then you go back and substitute again backwards. All right? So that's our third step here. If we pick u to be the inside function, usually will work if there's an inside function. If not, we can pick u so that the derivative is also in the integrand. That way, that piece will cancel out. And our third step is, don't forget, back substitution. In this particular example, step 1 worked. It was pick u to be the inside function, and the inside function was x plus 1. This was great. It was really great. But we wouldn't have been able to do it without remembering about back substitution. This is a very important trick in solving this, just an awareness of how the variables are relating to each other and what they can do next. So we'll do one more example, and then that'll be it. All right, I'm going to leave that other example up there just for now. I'm going to say, okay, I have the following integral. It's the integral of x square root 4 minus x. And I'm going to go through my procedure for u substitution, for how to pick my u. My first step is to see if there's an inside function and pick it. So that's exactly what I'm going to do. 4 minus x is my inside function. I'm going to pick that. I'm going to pick that as my u. That means my du dx is negative 1, or dx is negative 1 du. Substituting that in, I get x square root u times negative 1 du. And again, we're at this spot where we're like, man, we're so close, we're off by just 1x. And that's okay, because we pause and we say, oh, hey, look, if u is equal to 4 minus x, I can solve this for x. X is just 4 minus u. And I'll plug that in right here for my x. This becomes the integral of 4 minus u square root u times negative 1 du. I'll just pull the negative 1 out in front like I can do with any constant. And you might now be thinking to yourself, I still can't integrate this. It's a product. And you're totally right. We can't integrate it when it's written as a product. But we can do something really cool. We can just use some algebra and simplify it. This is a product, so I'm just going to distribute. This becomes 4 square root u minus u square root u. And I'm not going to write it like that because that's not helpful for me to integrate it. What I'm going to do instead is think, okay, this is u to the 1/2. This is u to the first. So this should become u to the 3/2. And now I'm in business because this root u is the same as u to the 1/2. This is u to the 3/2. I can just power rule this up. So the negative stays in front. This will become negative 4. And then add 1 to the power, bring the new power in front. 2/3 u to the 3/2 minus 2/5 u to the 5/2 plus some constant. And finally, u is 4 minus x. So I'll just plug that in here, here, and here. Oh, sorry, there are only 2 spots to plug it in. So I'll just plug that in here and here. And I'll end up with my final answer, which is, well, negative 4 times 2/3 is the same as negative 8/3. This will be negative 8/3, 4 minus x to the 3/2 minus 2/5, 4 minus x to the power of 5/2 plus c. Sorry, I kind of ran out of room there. Hopefully, this procedure of back substitution isn't too tricky for you. It takes some time to get the hang of, but the concept of it shouldn't be so bad, right? We substitute, we see we still have an x, so we back substitute, and then everything falls out really nicely as long as we remember some algebra, right? Tearing apart fractions into 2 separate fractions, or a distributive property. These things are very, very important. I cannot emphasize enough how important the algebra is when we're finding antiderivatives. It is so important, and if you don't feel like it's going so well, then I encourage you to go to your portal page. On there, there's a link to what's called OLL for online learning, and there's an OLL math section where some members of the department have put up various things like these videos, except geared towards algebra, geometry, and so on. Find an exponents one, go through it, see how it goes. Make sure that you're feeling good about these algebraic manipulations. I have total confidence that everyone here can do all of the calculus. Some of the algebra we've gotten a little rusty with, which is fine, just means we need to brush up. Okay? So that's all I've got for you today. Enjoy the rest of your evening, and I will see you in class tomorrow.